All right, hello everybody. Today is going to be devoted to a really wonderful data structure in computational geometry called the Voronoi diagram. And it's motivated by near neighbor searching. So the idea is that you have a collection of points, which for traditional reasons are called sites. And your goal is to be able to answer queries with an answer about which site is closest. Okay? So very, very obvious natural question, right? You're somewhere in town, you want to find the nearest post office. Where is it? Okay? And it turns out that there's a beautiful data structure for solving this problem. I will again start by asking, in computational geometry, we always start by thinking about reduced dimensions. So if you have a 1D problem, how do you solve it, and how long does it take? Yes?
Sort the sites and use binary search.
Exactly. Right? In one dimension, the nearest neighbor is just your predecessor or your successor. You put things into a binary search tree, and you check which one is closer, right? So order n space, order n log n construction, and order log n query time. Yes? So that kind of gives us our target, or at least something to compare to. How much harder is it to do this in 2 dimensions than it is to do in 1 dimension? Okay? So what I'm going to do is I'm going to sort of start showing you characteristics of this problem in 2D, which will lead us to thinking about what sort of geometric structure provides the answer. And then once we understand what geometric structure we need, we'll talk about an algorithm for actually constructing that geometric structure. Okay? So to start thinking about this in 2D, right, I'm going to talk about Voronoi regions. So in 2D, I'm going to say that V of pi is equal to the set of points that are closer to pi than any other site. Okay? So if you think about this, right, any collection of points, right, on the plane, right, and for any collection of sites on the plane, I can look and say which points on the plane are closer to site 1, which points of the plane are closer to site 2, and so on, right? And so I can just sort of label each, I can sort of divide up the plane according to closest neighbor, closest site. And this gives me a region for each of the sites. And that means that instead of having to ask which is the closest point, I can just ask what is the region of this query point, right? So the query now becomes what Voronoi region is the query point in. Make sense? So we're in a sense, if we take this perspective, we're not really going to be computing distances during a query. It's more of a point location problem. Which region are we in? Okay. So let's try to understand these regions. Okay. Intuitively, the region of a site seems to be, it seems like it should be, well, the stuff that's around the site, right? Like if you drew a little circle or box around the site, that would probably start to give you the Voronoi region for the site. But let's explore it a little bit more carefully. Suppose that I have only a single point, one site. What is the Voronoi region for this site? Yeah? It's the entire plane. That's easy, right? Suppose that I now add a second site. Now there are two Voronoi regions. What are they? What determines which Voronoi region a point is in? Which determines the closer site? Yes?
A line exactly equidistant between the 2 points.
Which is called?
What type of line?
It's called the perpendicular bisector, right? You draw the line between the 2 points, and then you take the perpendicular bisector of that line, and this defines the two Voronoi regions, depending on which side you are on of this perpendicular bisector. Yes? Okay. So 1 point. We have the whole plane. For 2, we're looking at the perpendicular bisector. What if we add a third point? Yes?
How consider 3 perpendicular bisectors?
Exactly. If we add a third point, well, really what's going on is we have 3 different pairs of points, right? And so for each of these pairs of points, we can draw the perpendicular bisector. Right? Okay. So a couple of issues here. First of all, I drew these 3 perpendicular bisectors intersecting at the same spot. Am I assuming too much? Right? I mean, maybe this third bisector needs to go off here somewhere. Right? How do why did I put them all through the same point? Yes?
Whenever 2 of them intersect, the distance between each of the 3 points of that intersection point is the same?
Exactly, right? At the intersection of 2 perpendicular bisectors, I have 2 equidistance constraints. And of course, that makes the third equidistance constraint apply also by transitivity. So in fact, all 3 points are equidistant. And what is this point if all 3 points are equidistant from it? Yeah? It's the center of a circle that involves all 3 of the points. Sorry, I'm not going to draw a good circle at all, but you see my point, right? So that is a very distracting line, so I'm going to erase it, but hopefully you take my point that there is this interesting circle that represents the intersection of these 3 perpendicular bisectors. Now here's another concern. I drew these 3 perpendicular bisectors, which created 6 regions, right? But there should only be 3 because there's 3 sites. So how do so what's going on here? Right? I mean, again, these perpendicular bisectors tell us, am I in the Voronoi region for this point or for this point? And this one tells me am I in the Voronoi region for this point or this point. And so there's kind of a combination thing going on, but why 6 and what do we do about it? Yeah?
So each point has a region that there's 2 slices, and the 2 slices are split by the line that corresponds to the other 2.
Exactly, right? So each of these points actually owns 2 of the 6 slices, right? And the slice that the point owns is split by the perpendicular bisector for the other 2 points, but we don't care because those other 2 points are both farther away. And so they're arguing over which of them is the second farthest point. which is not something that we're interested in. There's a notion of higher order Voronoi diagrams for looking at the second farthest point and the third farthest point, but we're not worried about that. So, for example, right, this point, it wins against this point on this side of this perpendicular bisector, right? And it wins against this point on this side of this perpendicular bisector, which means that in fact this divisor is irrelevant in the Voronoi diagram. And in a similar vein, this division is irrelevant in the Voronoi diagram. And finally, this one is irrelevant in the Voronoi diagram, right? So now we've got these 3 points, right? So our 3 bisectors meet at the center of a common circle, right? Okay, that's great. Let's do one more. I always get into trouble on the last one because there's too many ways to break symmetry. Let's see, why don't we try here and see what happens, okay? So now we again have all of these different perpendicular bisectors to worry about, right? So let me get rid of these that I was looking at before. Okay, so we've just added a point. And actually, this is an algorithm you could consider implementing, although we're not going to do it this way. But let me draw now this perpendicular bisector. And this perpendicular bisector. And this perpendicular bisector. Okay, and they're all meeting down here at the circumcircle of this point, of these 3 points, right? And so again, I've drawn too many lines because there are parts of these lines that don't matter, right? So really for this point that I've added, this is important. This defines the Voronoi region for this new point, right? And the rest of these bisectors is not important, right? So I think we can do away with this. This is still here. This doesn't matter. This one doesn't matter. So we'll have something that looks kind of like this, right? I think that's about right. Okay. So the Voronoi diagram, sorry, question?
Can't you just, for each point, figure out which ones it's involved with and use those as boundaries? Like, you have to go to...
Yes, that's essentially what I'm doing here.
And they're still redundant.
What was that?
They're still redundant.
Well, again, I started by drawing the whole bisector, and a lot of that is redundant, right? And I was doing that just to show you how I was figuring this out, right? One more thing I should show, though, is that as I add some more lines, so right now all of these regions are open, right? But as I add some more points, I can end up with closed regions. And I'm not going to draw the whole Voronoi diagram at this point, but things might start to close off based on other points, right? If a site is surrounded by other sites, for some appropriate notion of surrounded, then its Voronoi region is going to be bounded. Make sense? All right. So here you can see I've sort of started sketching out this Voronoi diagram for this set of sites. And I mean, I'm sure it's wrong in the details, but hopefully this gives you the idea of what a Voronoi diagram can look like. So what are some things that we can say about these Voronoi regions? There's one thing that's kind of immediately clear just because of the way they're constructed. So notice that each Voronoi region is an intersection of half spaces, right? Essentially, right, the Voronoi region for me is the half space. There's a half space that I win against each other point. And so if I intersect those half spaces, I get the region that I win against all of the points. So so an intersection of half spaces has what characteristic? Yeah?
Can be described by matrix A times X less than
Oh, that's algebra. I don't do algebra. I'm sorry. Geometry. Yes?
It's a polytope?
It's a polytope. It's a convex body, right? It's an intersection of constraints. Yes? So that's nice to know. It's not actually essential for what we're doing, but it's a nice observation. So if we can build the Voronoi diagram, okay, this division of the plane into these n regions, okay, one for each site, now the point location problem, now the nearest neighbor problem is just a question of which Voronoi site, which Voronoi region am I in, right? Which of these n convex bodies am I inside of? Okay. Is it easy for me to answer that question? Right? Like if I build you this set of regions, can we maybe come up with a data structure that can quickly tell me which region a query point is in? Yes?
Yeah, we already did this before with the persistence.
We did this, right? Okay, that was lecture 2. It's one of the reasons I did lecture 2. Okay, is that it gives us the answer to this problem. Anybody remember the performance of that data structure? So it was very nice, right? It basically took n log n time to build the data structure. It took n space to store the data structure. And your query time was log n, which is wonderful, right? Because that's exactly the times of the one-dimensional nearest neighbor problem. And here we are solving the two-dimensional nearest neighbor problem. But there's a but. What's n? I'm going to use a capital N. Yes.
The number of intersections of those lines?
Yeah, well, sort of. So it's not just the number of intersections of the lines, it's the size of the arrangement, right? It's actually sort of the number of line segments in this data structure. Okay. And that's a little worrisome. We don't know anything, we haven't proven anything about the number of segments in this data structure. So that's actually going to be our first step, is to put some quantities on the complexity of the Voronoi diagram. Okay, so we're worried, right? Because we have n points, which means how many different perpendicular bisectors? N squared, right? And if there's n squared of these line segments, if all of these perpendicular bisectors show up, then these are no longer good numbers. Right? So let's talk about the size of the Voronoi diagram. Okay. So the first thing that I'm going to observe is that the Voronoi diagram is a planar graph. Okay. If I think of the, and I should say that the vertices are these intersections of 3 of these perpendicular bisectors, right? And these are called the Voronoi points. Okay. And so the vertices are these Voronoi points, and the edges are segments of these perpendicular bisectors that end at these Voronoi points. Okay. But this means that no 2 edges cross in the picture. Why can't 2 edges cross in the picture? Well, if this is an edge and this is another edge, then what is this crossing point? Yes?
Equal distance to 3 points.
Exactly. This is so if they did, then their intersection is a Voronoi point. And so that actually would split the line segment, that would split the edge into 2 edges. So wherever there's a crossing, it's actually a meeting point of 4 edges. Make sense? So the edges don't cross. So we have a planar graph. And what's nice about the planar graph is that there's this famous formula due to Euler. Which says that the number of vertices of a planar graph minus the number of edges of the planar graph plus the number of faces of the planar graph is always equal to 2. Okay. And we know what vertices and edges are. What's a face of a planar graph? Well, it's a region. Okay? It's one of these shapes that is outlined by a bunch of the edges. Question?
Does that include the ones that are the infinite-sized ones?
Yes. So the way you make this work when there are these open regions is you imagine a point at infinity. Okay? Or another way to do it is to imagine that the plane is actually a sphere. So all of these lines that stretch out forever, they actually wrap around to the back of the sphere where they all meet at the point at infinity. Okay? And that point at infinity becomes the other endpoint of all of the edges that go on forever. And so that is one more vertex of your planar graph, is that point at infinity. Okay? So let's prove this. It's a pretty nice induction. what I'm going to do is I'm going to start with any planar graph, and I'm going to simplify it without changing the value of Euler's formula. And when we're done, it's going to be 2, which will tell us that it was also 2 at the beginning. Okay. If you have two faces separated by an edge, what happens when I remove the edge? So if I have a shape like this, and I have an edge running across, right? If I remove this edge, what does it do to Euler's formula? Yeah?
Increase in edges by 1 and then faces by 1, so it stays constant.
Exactly. We decrement the number of edges, and we decrement the number of faces. And so Euler's formula has not changed. Okay? If we have a degree 2 vertex, okay, how can we simplify? Yeah?
Vertex and 2 edges for faces.
Well, it's not about merging faces. We'll just remove the vertex and turn it into one edge. Okay? What does that do to Euler's formula? Yeah.
Well, it decreases the number of vertices by 1 and number of edges by 1.
Exactly. Okay, and the last case that we're going to think about is sorry, that's actually all we need to do. Okay, basically, as long as we have a degree 2 vertex, we can simplify using this rule. Okay, once we have no degree 2 vertices, right? We will have the thing that we can't do in this situation, or at least not clearly, is remove an edge here, because we would leave a vertex kind of hanging off in nowhere, and it's not exactly clear what that would mean. But once we get rid of all of the degree 2 vertices, now we have a graph where every vertex has degree at least 3. So now we'll just take an edge. Both of its endpoints have degree at least 3, so when we remove that edge, we're creating this merger of two faces. Okay? So we can always apply one of these two rules in order to simplify our planar graph without changing Euler's formula. Okay? And the number of edges keeps dropping. Eventually, we only have 2 edges, right? Which means we're going to have to look like this. That's the only way, that's the only planar graph with 2 edges. Okay. And now we can just sort of brute force, just sort of directly inspect Euler's formula, right? We have 2 faces, we have 2 edges, and we have 2 vertices. So Euler's formula is correct. Okay. And since the final value is 2, and we were changing the value, it means the original value was 2 as well. Any questions? All right. That was just some pure geometry or graph theory. Let's apply that to our Voronoi diagram. Sorry, was there a question?
Here we also consider an infinite vertex, right?
A vertex at infinity, that's correct.
Then we have 3 vertices.
No, I've already removed it, right? So this is, again, when I'm doing this analysis, I don't really have to treat the vertex at infinity as anywhere different. Like I can draw it in my picture, right? And so it's just another vertex that could get removed at some point. What I'm being careful to do, again, is to leave no exposed, like, an edge with an endpoint that only has degree 1. Right? But whether it's the vertex at infinity or not doesn't matter. It's treated the same as all the other ones. Right? I mean, think of it this way, right? So I draw this graph, and one of its vertices is labeled edge at infinity, right? Or vertex at infinity, right? Now, what that actually represents is that I have some graph, and I have a whole bunch of edges flying out into nowhere land that go to the vertex at infinity, right? But when I want to draw this graph, I'll just put infinity here, right? And say, OK. Two edges that what?
If the graph is not simple, use the formula. If we have two edges between two vertices.
Yes, when you have two, that's exactly what's going on here, right? Since I have two edges between these two vertices, they create two faces. Okay, so it does handle parallel, and I mean, if I add another edge, I'll also create another face. So it works fine for parallel edges as well. Okay. All right, so let's apply this. So we need to understand in the Voronoi diagram what corresponds to number of vertices, number of edges, and number of faces. Okay, and so now I'm going to be careful to talk about sites of the Voronoi diagram as opposed to vertices of the Voronoi diagram, right? And so what are the vertices of the Voronoi diagram? I already gave them a name. Yeah. Exactly. The vertices are Voronoi points. And what are the edges? Well, let's start with easier. What are the faces of the Voronoi diagram? Yeah. Faces are, they're not points.
Well, I guess there's one face for each side.
And what is that face called?
The Voronoi region.
Exactly. And then we've got the edges, right, which are the region boundaries. Now, can we assign some numbers to these? Okay. So what is the number of faces? Yeah?
Plus 1.
Why?
Because we have our n regions, and then there's one n. No, not the perfect. Sorry, so just that.
Exactly, right? Each face is a Voronoi region. There's one for each site. Okay, that's great. Now we can also notice that every Voronoi point which is to say every vertex of this graph has degree at least 3. Why is that?
Because every face is convex.
What was that?
Every face is convex.
So I don't know that it follows directly from convexity because, I mean, I could imagine. Oh, I see what you're saying. Yes, that's actually a valid argument, right? We said that the Voronoi regions are convex, and if I only have two edges incident on a Voronoi point, one of my angles is going to be larger than 180 degrees, which is going to create a concave shape. Okay, so yeah, I'd have to worry about what if it's exactly a straight line, and that can't happen. That is a very strange case, right? What happens in general? Yeah.
So in general, we said like the vertices are an intersection of three bisectors.
Exactly. So there are, as I drew up here, in general, each of these Voronoi points is defined as the intersection of three perpendicular bisectors. Okay. I don't think that you can actually do this. Well, let's see. Maybe I can do it like this. Yeah, something like that. So the caveat I'm going to add here is assuming what we call general position. Okay. General position says that the points aren't kind of perfectly aligned to make pathological situations. In particular, no four sites can be on a circle. Okay? If you have four sites on a circle, then all the perpendicular bisectors for all those pairs meet, and you would have a degree 4 vertex. In general position, every Voronoi point actually has degree 3, except for possibly the point at infinity, right, which could be much larger than 3. Okay. Now, the other thing I'm going to notice is much more obvious. Every edge has two endpoints. Okay. So we're going to put these things together. Right? So we know that every edge has two endpoints. So one way, so I'm going to count edge endpoints. Okay, how am I going to do that? Well, one way I can count edge endpoints is for every edge, count its two endpoints. So that gives me 2 times the number of edges as the number of edge endpoints, right? But another way that I can do it is take every vertex and count up its degree. Right? That's another way of counting all the edge endpoints. And that is going to give me 3 times the number of vertices plus 1. Okay, as another, or sorry, this is greater than or equal. Because every vertex, along with the point at infinity, has degree at least 3. So if I only count 3, I'm undercounting when I do it this way, whereas I'm exactly counting when I do it this way. Okay? So now that I've counted these both ways, right, so now I'm going to use Euler's formula. Okay? Euler's formula related all these different quantities. And in particular, I can replace the number of edges by all of the other quantities that show up in Euler's formula, right? So the number of edges is the number of vertices plus the number of faces minus 2. So that's what I'm going to write. N sub v plus n sub f minus 2 is at least 3 times nv plus 1. Okay. But now, remember, we said that the number of faces is equal to n. So I'm just going to erase that f from this formula, which finally gives me a relationship between the number of sites and the number of Voronoi points. okay? And if I solve for that, I find out that n minus 2 is at least nv plus 3 over 2, or in other words, the number of Voronoi points is at most twice the number of sites. And once you plug that into Euler's formula, you find out that the number of edges is at most 3 times the number of sites. So the end result summary of this is that the Voronoi diagram has linear size. The number of Voronoi points and the number of Voronoi edges is linear in the number of sites, right? Capital N that I drew before is order little n. And so all of these runtimes that I claimed over here are exactly the runtimes that we want. N log n to construct, n space, and order log n query time. So from the Voronoi diagram, you get an optimal nearest neighbor data structure. Question? Ah, yes, one more little detail. How do we find the Voronoi diagram? Right? But what I've shown you is that if we could build the Voronoi diagram, our problem would be solved. Right? Is that your question as well? Yeah. Okay, so we have this one remaining burning question. How can we actually build the Voronoi diagram? That seems like a great time to take a break.
I know it has a name. It's a Delaunay triangulation. Yes. But I've forgotten what property Delaunay triangulation satisfies. And I know, I'm just trying to figure it out. Yeah, I hate when that happens because whenever I can do the random variation in the future, I always think, is it because I graphed it at one day? Other than that, it is the graph that can be made by taking a dual. For example, how will you check, given a time relation, whether it is one other than corresponding or I feel like there's something to this.
Well, the circumcenter of any triangulation would be the
I know there's like a one sentence description of what I do. Interesting thing is
no.
I didn't like dual. I don't like dual.
Wait, I don't like computing LP.
Yeah, fine.
I like the concept of duality.
So, another question I was wondering is, if you take a graph which you want to solve, like you plug in, like checking the overview equation here, and checking if there's a TSP, or like problems on the graph. you have a PSC problem.
Is it like,
Right, no, a PSC. Let me think what I said. You have, no, let me, this might take too long. Basically, I don't believe all, so if you take an entity graph and you make a new graph where the n is a node, and you connect n with the k, right? They share a vertex. This is not a, you cannot make a new graph.
this is not a surjective function graph?
Yeah, I don't think so. Because I think if you were to be able to solve PSC,
Any, try, any, I want to say if you have, I want to say if you have 500 vertices and all but one of those pairs is then you ask for each vertex of your new graph. If two vertices of your graph is connected by an edge,
So I've now demonstrated, hopefully, how wonderful the Voronoi diagram is, right? And all that's left is the problem of constructing it. And I mean, it's funny. So far what we've done has definitely been geometry, but it hasn't really been computational geometry because I haven't given you any algorithms, right? I've just been studying this geometric artifact. But now we need an algorithm to construct this geometric artifact. And that's typical in computational geometry. Often the output of the algorithm is a geometric artifact, right? We looked at the convex hull problem last time. Now we're trying to output the Voronoi diagram. So, one sort of sledgehammer approach actually reduces the Voronoi diagram to the convex hull problem in 3D. So it turns out that the Voronoi diagram is the graphical dual of the projection of the convex hull of a lifting of the sites onto a parabola of revolution in the third dimension. Done. Okay. It's a great sentence, isn't it? Right, so basically, you take your plane with all of the points on it, and you draw this big parabola up here, and you send all the points up to where they hit on the parabola. And then you build, this gives you a bunch of points floating in a 3D space, and now you build the 3D convex hull of that collection of points. And if you think about it, that 3D convex hull is going to be a polytope, right? So there's going to be some vertices, which are the lifted points. And there's also going to be some edges connecting those vertices and some faces of that 3D polytope. You just take all of those lines from the 3D polytope, and you project them back down onto the plane, okay? And that will give you a planar graph, okay? Because the convex hull is a polytope. It is a planar graph. So when you project it down, you still get this planar graph. And you take the dual of that planar graph, which is not something I've defined for you yet. But it's actually, the dual of the Voronoi diagram is interesting in its own right. To take the dual of a planar graph, what you do is you put a vertex in each face of the planar graph, and then you draw an edge between any pair of vertices that are neighboring regions in the Voronoi in the planar graph. Okay. So this is a dual process because you start with a planar graph, you construct a different planar graph, And if you take the dual of the new planar graph, you get back the old one. Okay? Now this dual planar graph is something that's known as the Delaunay triangulation. And the Voronoi diagram is cool. The Delaunay triangulation is also cool. So what the Delaunay triangulation does is it gives you the best mesh over your points. So when you're doing simulation, right, in wind tunnels or whatever, of wind tunnels and so forth, right, you'll take this artifact and you'll model it as a collection of points. And you then run simulations by sort of looking at the state of each point and seeing how it influences the state of the other points nearby. So there's a lot of messages going back and forth between points and their neighbors. And the quality of your simulation is affected by the quality of your mesh. And what you want to avoid is long, skinny triangles in your mesh. If your mesh has long, skinny triangles, then neighboring points may be very far away from each other. And that means that they're too different. And the information that they pass back and forth in the simulation is not accurate. Okay? It's also bad for rendering. Like in computer graphics, you don't like long, skinny triangles. Their aspect ratio is bad for similar reasons. So a question which got asked a long time ago is, here's a set of points. What is the best triangular mesh that I can put on these points? And that is called the Delaunay triangulation. It is the mesh with the largest minimum angle of in any triangle in the mesh. And it turns out, the world is magical, that the dual of the Voronoi diagram is the Delaunay triangulation. Okay? And again, this makes the Voronoi diagram even more important because the algorithm for constructing the Voronoi diagram is also the algorithm for constructing the Delaunay triangulation that you need for your simulations and rendering and so forth. So we're getting a lot of things all at once by looking at this problem. Okay? So I guess technically, the Delaunay triangulation is the projection of the convex hull, and the Voronoi diagram is the dual of that. Okay? So that's really great, and is a very short cut to an algorithm, except I didn't tell you how to do 3D convex hulls. I only taught you 2D convex hulls. So we're going to look at a different algorithm for constructing the Voronoi diagram. And again, there are, I think, like 7 or 8 different algorithms for constructing the Voronoi diagram. But the particular one that we're going to look at is a sweep line algorithm. Okay. So we talked about sweep lines last time. Just to keep things interesting, I'm going to do the sweep line entirely different this time. This time, the sweep line is going to be horizontal and move vertically. Okay? And we're going to use this sweep line idea of sort of move the sweep line down and build the Voronoi diagram at the sweep line. Okay? We want to have the Voronoi diagram built, the part of it that we know about, built above the sweep line. And then as we move the sweep line down, we'll bump into more points, and we'll have to sort of add those to our Voronoi diagram. And then once the sweep line has moved all the way down, we'll have the entire Voronoi diagram. Okay? So again, roughly speaking, what we'd like to do is have the Voronoi diagram above the sweep line and not yet know what the Voronoi diagram is below the sweep line. Unfortunately, it's not quite that simple. Okay? Suppose that I know all of the points above the sweep line, all of the sites. Does that tell me what the Voronoi diagram is above the sweep line? All right. Let me make myself some more room. So here's my sweep line, right? I've got this collection of points, right? I can presumably, have the Voronoi diagram built up here. Right? But do I know the whole Voronoi diagram above the sweep line? Yeah?
No, because the next point might be right under it, in which case.
Exactly. I may think, ooh, great, you know, this is my Voronoi diagram. But what if there's a point right here? Right? That point might own some of the area above the sweep line and change what the Voronoi edges are like above the sweep line. Okay. So the first question I'm going to ask is, given the points above the, or the sites above the sweep line, what part of the Voronoi diagram is fixed or known regardless of what is below? Yeah? Well, if the region has closed, then yes, right? That can't change later, because essentially what you've said is, you know, there's these sites around me, and you know, I'm the closest to this region, and anything outside of this region, you know, whatever direction I go in, some other site is taking over. So I already know it's not mine. And other people, like other points, are going to be farther away than the ones that surround me, so they're not going to change what's mine. Okay, but that's only part of what is known. Yes?
Maybe we can imagine there's points along the entire and
Great. So suppose there were points, an infinity of points, right? That's kind of the worst case, right? Is that actually there's an infinity of points here that are taking away as much as possible of the Voronoi diagram above the line. So what part of the space would all of these points own, right? Or to invert it, right? What parts of the space do we know that this point owns regardless of what's below the line? Yes?
The points above the perpendicular bisector of that line and the form.
Okay, so yes, essentially what we need to think is that anything that's closer to the point than to the line, we know that point we know that nothing on the other side of the line could possibly take that away from this point or from whatever point owns it, right? So there's a portion, there's a region up here that we know the line can't affect because it's closer to this point than to this line. Now you said perpendicular bisector, but what is the set of points that is closer to this point than this line? It's not defined by, right? It's not defined by this line. What is the boundary, right? Well, the boundary is the things that are equidistant between this point and this line. What shape does that boundary form? Yeah? A parabola. Exactly. So the part of our Voronoi diagram that is known is what's above a collection of parabolas defined by the sites that we've seen. Okay? Right? Where basically the requirement, the equidistance is defined by a formula that says the distance from the focus of the parabola is equal to the distance from the line. Okay, so I'm going to define, t is going to be the variable representing the height of my line. And once I fix t, once I fix the line, I get a parabola in x versus y, or in y versus x, that is determined by the focus, and also, which is the site, and also by the position of the line. Does that make sense? Now, the guy who developed this algorithm is named Steve Fortune, and he decided to be poetic and call this the beach line. Because imagine now, and we're gonna add some numbers to this in a minute, but imagine that the line goes down, right, as we sweep the line down. What happens to the parabolas? Well, the parabolas are also going to go down, right? The line's getting farther away, so the foci have more control. They control a larger region. So essentially, you've got these ripples of all these parabolas that are just flowing down the screen, sort of trailing behind this sweep line. And so that parabolic boundary is what we're going to call the beach line. Okay? And so the sweep line is driving things, but what we're actually going to do is see what's happening at the beach line. And we're going to build the Voronoi diagram at the beach line as it moves down. So let's understand that descent of the beach line. So up there I have a formula for a particular parabola, for a particular site. And my question is, what happens to that parabola as the sweep line descends? Okay. So in order to answer that numerically, I'm going to differentiate the parabola formula. Right? If I take d by dt on both sides, right, what that tells me is that 2 times y minus yf times dy dt plus, whoops, sorry. I'm going to do this at a fixed x. Okay? So I've got this parabola, I've got this sweep line coming down. I'm going to ask, what happens at this value of x? How does the parabola descend at this value of x? Okay? And since I'm fixing x, that doesn't show up in the derivative. I just understand how y is evolving for that x. And on the other side, I have 2 times y minus t times dy dt minus 1. Okay. So there's my implicit differentiation. I solve for that, and I find out that dy dt is equal to y minus t divided by yf minus t. Okay. And the exact formula isn't important. What I want to take away from this is that if I have a higher focus, yf, then the parabola descends more slowly. At all points. Okay. So actually, let's now start mapping out some cases. Okay. So this formula sort of tells me what happens as long as I've only got one site, right? I've got this sweep line, and it's descending. And the parabola that's defined by this focus and the sweep line is also going to be descending, right? And this midpoint is going to be descending exactly half as fast as the sweep line is descending, and these other points are also all going to be descending. Okay? Now, what happens when I encounter my next point? Okay? The sweep line is going to hit a point. How does that change my beach line? Well, initially, this point is going to own sort of only itself, right? But as the as the sweep line continues to descend, you're going to get what is initially a very narrow parabola that breaks the previous parabola into two pieces. Okay? So the beach line was previously just a single parabola. Now the beach line becomes three segments of parabolas. Okay? And this is what is called a site event. Okay? The beach line hits a new site. Sorry, the sweep line hits a new site. And this splits a parabola with a new one. Okay. Now, let me point to some interesting topological things on this parabola. Right? So we have these points which are intersections of two parabolas. What are those points? What's interesting about them? What is unusual about these points that are the intersections of two parabolas?
They're on the perpendicular bisector.
They're on the perpendicular bisector, right? The intersection of two parabolas, well, the points on the parabola are equidistant from the line and a focus, right? So if you're equidistant from this line and a line and this focus, and you're also equidistant from the same line and a different focus, it means you're equidistant from the two foci. Okay? In other words, you're on the perpendicular bisector. And in fact, as the two parabolas now descend, right, the intersection point is going to evolve, and it's actually going to trace out the perpendicular bisector between the two sites. Okay. Now you notice from this picture, again, this is a little counterintuitive. I actually taught this wrong for several years. One of these intersection points is going to go down, right? But the other intersection point is actually going to go up as you trace out the perpendicular bisector. Okay, so even though the sweep line is going down, the part of the perpendicular bisector that you're tracing is going to go up. Okay. Good. Now, what happens the next time I hit a site? Sorry, is that the question I want to ask? So the introduction of this new site sort of introduced an intersection point, a perpendicular bisector, which, at least for now, is something that needs to be in the Voronoi diagram, right? So tracing out this intersection point is tracing out one of the Voronoi edges, right? Now, besides the sort of introduction of a new site as the sweep line hits it, is there anything else that can change the topology, the sort of what parabolas we're dealing with or what pieces of parabolas are on the beach line. And I'm saying topology because obviously as the sweep line goes down, all of the parabolas are going to change. But if they're sort of ordering of which parabolas are touching which parabolas doesn't change, then the topology hasn't changed. Yes?
I think you can close off some of the parabolas if you have like two perpendicular bisectors that meet like this.
Good. So the other interesting thing about this tracing is that you could actually stop a line, right? You can start lines. You can start Voronoi edges, but you can also stop them. And let's think about what could cause that to happen. Okay? So, sorry, my notes went shy. What is going to make a Voronoi edge disappear? Okay? Is it just going to suddenly stop? Well, if you think about it, a Voronoi edge is going to stop, right? So it's getting traced out, right? It's going to stop at a Voronoi point, right? What defines that Voronoi point? Well, it's the intersection of three Voronoi edges. So what's actually going to happen is that two Voronoi edges that are getting traced out are going to collide with each other and turn into one Voronoi edge. But let's think about how that happens in terms of the parabolas. Okay. So what sort of tracing or what sort of parabola shapes cause this to happen? So let me start by asking, here are these two parabolas which are descending and are tracing out this Voronoi line. Okay. We need to have some other parabola that is descending and tracing out a Voronoi line, right? And they collide, and suddenly there's only one Voronoi line. Why did that happen? What happens to the parabolas?
Oh, the middle one like disappeared behind the two.
Exactly, right? So this is what is known as a circle event. Strange name, we'll have to ask why that is, right? A circle event happens when one parabola vanishes behind two that are descending faster. Okay? And if you think about, like we did this differentiation, it's going to be the highest one that vanishes. And the reason is that it's descending the slowest. Okay? So at the moment that that happens, right, what's going on with that vanishing is that the highest parabola is disappearing behind the intersection of the other two. It is also intersecting that intersection of the other two. Okay. And what does it mean when three parabolas are intersecting? What is that intersection point of the three parabolas? Yeah? That is a Voronoi point, right? It vanishes at the intersection. Which is a Voronoi point, which is, of course, the center of the common circle. So that's why it's called a circle event, is that you've just found the center of one of these circles that is important for the Voronoi diagram. Now let me ask you something. Why did I make a parabola disappear behind two other parabolas? What if I had a situation like this? Could I have one parabola disappearing behind one other? Yes?
I think that's impossible because the one that's higher will always kind of be wider.
Correct, right? This doesn't happen. Instead, you're always in this situation, right? The higher parabola is wider, and it descends slower. It never overtakes the narrower parabola in order to make it vanish, right? So in fact, it's the other way around. The narrow parabolas appear. Those are the sight events. Okay, they never disappear behind another parabola. Okay, the only way for a parabola to disappear is when it's caught behind two of them, and you're tracing out, you're arriving at a Voronoi point. Okay? So the summary is that you have these sight events, which adds a parabola to the beach line. And if it's adding a parabola, right, it's also adding two intersections to the beach line, which correspond to two Voronoi edges. Okay? And so that's what happens as you descend and one Voronoi edge splits into two. Okay? The circle events are the other way around. Right? Those remove a parabola. And those correspond to this situation where you've got two intersections being traced out, and it turns into a single intersection. Okay. So that's the cartoon of the evolution of the beach line as the sweep line descends. All we need to do to finish is to sort of implement this tracking algorithmically. And what do I mean by that? I mean that we have this series of events at various values of t as the sweep line is going to down, right? And what we need to do is process them in order to detect new Voronoi points as they appear, okay? And edges between those Voronoi points. Okay. So what we're going to do is we'll use a priority queue of these events of sort of of where things happen. And what are these events? These events are appearance of a new parabola, and disappearance of a parabola. And we're going to, pull the next event off of the priority queue and update our Voronoi diagram, our partial data structure, right? But what we're also going to have to do is predict future events and put them in the queue. Now, some of the events that are interesting to us, we know at what value of t they happen even before we start running the algorithm, right? What are the events with known times right at the beginning? Yeah? The site events, right? So the site events are known. The problem is the circle events, right? It's, again, there's n-cubed circles that might be relevant. Which ones do we need to keep track of? So when does a circle event happen? It happens when we have a situation like this and the middle parabola falls behind, right? Now you'll notice that what this means is we have 3 adjacent pieces of the beach line, and the middle piece is disappearing. Okay? Which tells me that the only circle events involve neighbors on the beach line. So, in order to detect these circle events before they happen, when we still have time to put them into the priority queue, what we will do is track the order of the beach line segments. In a binary tree. Okay. So, I'll have some beach line, and all of a sudden, a new parabola will appear during a site event. What I will ask is, if I sort of binary search through these parabolas, where is the one that I am directly underneath? Okay? That will tell me where I need to take a current segment of the beach line and split it into 2 segments to make room for my new parabola. Okay? So on a circle event, I insert a parabola into this tree. Okay. And this creates new neighbors. Which might end up in a circle event together. So I compute where the circle event will happen for these new neighbors. And I put that into the priority queue. Okay. Similarly, when a circle event happens, I take a parabola out of this beach line, and that also creates some new neighbors because there were some segments that were previously not next to each other that now are. Yes?
Can you repeat what happens in the last figure?
In this figure.
No, the one with this small shape.
Yes. So if this is my existing beach line, right, when there's a site event, I introduce a new parabola into the beach line. So that new parabola is actually going to split one of the existing parabolas and create a new, it's going to turn one segment into 2 and put a new segment between them in the beach line. So I need to update my list of segments to include this new segment. Okay, sorry, I see I've gone over time. I'd hoped to finish Voronoi diagrams completely, but I think there's enough still to do that I will take 10 minutes at the beginning of next class to finish that. That will also end our geometry section, and our next topic, which we start on Friday, is going to be online algorithms. Okay, so I will see you then.